So today I'd like to do what I think will probably be the last tutorial in my 65-bit16 assembly series. And what I'm going to cover today are how we handle records or structures and pointers. So the problem for today, if you recall with the previous video, we really only dealt with one sprite up to this point, just the player's ship. What we'd like to do is to be able to manage multiple sprites of different types. So with a player sprite, you might have a target or an enemy vessel sprite, and then torpedoes or missiles or whatever. Each of these things will need to behave in a different manner. So you want to have different game logic for those sprites. But then you also need to be able to track the position and direction of motion for all of those sprites individually. And so that's what we're going to try to solve today in the game, and that's what we're going to try to solve with records and pointers. Let's start off with structures first. We'd like to track a bunch of different pieces of information about each of the different sprites or game objects that we're going to have on the screen. The position, where is it moving, is it active, what kind of thing is it, that sort of stuff. To try to keep track of all that information, it's handy to have some way of doing a structure or a record. Now this is going to be something that is very specific to 64 tasks in this tutorial. Some assemblers do have some way of defining a structure, others do not. Really behind the scenes, all that you're doing is you're defining some labels. Labels for addresses, labels for amounts of offsets from a particular memory location, that sort of thing, for different members. That's what you're doing behind the scenes. The structure is just sort of syntactic sugar on top of that. But because we have that in 64 tasks, we'll use it, and it'll make it a little bit easier to read and understand. But this is stuff that you could handle even in a very simple assembler that really only has labels. So in 64 tasks, there are three main assembly directives for working with structures. You can declare a structure with .struct and .ends, which stands for end structure. Really, that's just brackets, kind of a begin and end keywords for the structure itself. And you would put the members or the instance variables listed inside them, and the way that you would do that is you provide a label for each member and then use an assembler directive to indicate how big that member is. There are several different things here, but the main things that we're going to be looking at are .byte, .word, .long, and .dword, which are 1 byte, 2 bytes, 3 bytes, and 4 bytes in 64 tasks. And then actually instantiate a structure, you would use .destruct. So I have here just a quick little example of what a structure definition looks like in 64 tasks. HW sprite .struct. This is saying I am defining a structure called HW sprite. Inside it are four members: control address X and Y. Control is a single byte. Address is long, so 3 bytes, and X and Y both are words or 2 bytes each. The question mark that you see there, when you're working with those, the .byte, .word, etc., assembler directives, you can provide a value in many instances, and that is the default value that variable or location is going to have. In this case, when we're defining a structure, I suppose you could put a default value in there, but we really don't care in this code's case. So I put a question mark in there to indicate that there's no particular value to put in there at startup, and that the code itself will take care of that. So one of the things that would be nice to be able to do in this code, for example, the function to update a sprite, it would be nice not to have to code that function for every single sprite in the system up front, but to be able to pass a pointer to a sprite into that function and have it work with that data. And so that's why we're going to be wanting pointers and getting into how to handle those. And this is going to require that I introduce 3 more addressing modes. And these are all the indirect addressing modes. So there is indirect, plain indirect. There's indexed X, indirect. And then there's indirect indexed Y. All of these operate in the direct page. And the operand is indicating an address in direct page, and the data in that location is serving as a pointer to some other location in memory. In the 65-bit16, these pointers can be either 16 bits wide or 24 bits wide. And we'll be using, in the assembly syntax, parentheses to indicate 16 bits and square brackets for 24 bits. So let's take a look at the simplest case first, which is just plain old indirect. In this one, the operand is a memory address, and that memory address is specifying the actual pointer to the data that we want. So in this example here, I'm doing a LDA square brackets of 8. The square brackets are indicating that we're doing a full 24-bit pointer there. So we take that 8, and we add it to the direct page register, which in this case is 102, and that gets us an address of 10A. And that is the address of the least significant byte of the 24-bit pointer. And the value that we have there is 123456. And that is the effective address for this instruction. So if we go to 123456, the location there contains the value BC, and that is the value that we're going to load into A. There is also a 16-bit version of this instruction, which would use just plain old parentheses. I have not charted that out here. The next 2 examples, which are a little bit more complicated, are both 16-bit, so you'll see those there. But this one has that as well. But anyway, what you see here with indirect is that we have a pointer there in location 8 in the direct page. And we're just dereferencing that pointer and getting the value that that's indicating. Next is more complicated, is indexed X indirect. Now, I'm saying that very deliberately because I'm always getting these 2 addressing modes, the names confused, because the order is important on those words. In this case, our operand is indicating the location of an array of pointers, and we're using X as an offset to the desired pointer. Actually, I suppose I should say that the operand is specifying the starting address of a block of memory that contains some data, and that X is the offset into that data that is indicating a pointer, because we could have other things there as well. The way this is written is we have LDA paren 5 comma X close paren. So this is indicating that we first do an offset by X off of 5, and then we're dereferencing it. The parens are representing that dereference operation. So the first thing we do is we take 5, and we add that to the direct page register. That gets us 107 so far. But then we also add on the current value of X. In this case, that's 3. And that gets us the address 10A. And that is the location of the pointer in memory. So we need to then look at the address that's there, and that's what we're going to use as the effective address. Now, in this case, because I'm using parentheses, I'm indicating that this is actually a 16-bit instruction, not 24 bits, what you might call a near version of this. So we're only going to take the first 2 bytes from those memory locations. So we take 3, 4, 5, 6, and because this is 16 bits, we need to look at the data bank register. That gets us, in this case, 13. And so our final effective address is 133456. So 3456 is coming from the direct page pointer, and then 13 is coming from the current data bank register. So we look in 133456, and what's contained there is BC, and that's what we load into the accumulator. So you can see this is quite a complicated instruction in terms of all the different things that are happening here. Where this can be useful is As I said, if you have, say, an array of pointers, X can be used as the index to the particular pointer that you want. If you have a structure that contains a pointer, X can be used as a way to find the pointer in that structure, so long as that structure is in the direct page. Things along those lines. But basically, the indexing part is happening before you do the indirection, and that's why the words are in the particular order they are in the address mode name. Next is indirect indexed Y, and notice here that the order is different. We're doing the indirection first, followed by the indexing. And in this case, your operand is providing the address location of a pointer. That pointer is pointing off into a memory block, and Y is the offset within that block of the data that we want. So let's say we do LDA 5, comma Y. So you see here, comma Y is outside the parentheses. So we take the 5, we add it to the direct page, that gets us 107. So now we go to 107, and we need to look up the pointer there, and that is 3456. So we take 3456 and we add the current value of Y to it. So we add, in this case, 3, and that's going to get us 3459. Now again, this addressing mode, you can either do a near 16-bit operation with parentheses, which is what we're doing here, or you can do a far indirect indexed Y operation where we'd have square brackets. Because this is near, we're just using the 16 bits, and we need to look at the databank register. So we take the databank register, which again in this case is 13, and we tack that on to the 16 bits we had from the previous calculation, which is 3459. So the final effective address is 133459. We look in that location memory, we have BC there, and that's what we load into the accumulator. So you see here, the indexing operation where we add the Y to the address happens after we have dereferenced the pointer and gotten 3456 as the address to start with. Where this can be handy is if you have a pointer to an object anywhere in memory and you need to look at a particular section of that object. Let's say it's an array of something, to look at the fifth item in that array, or if it's a record, if it's a structure, to look at the member that's at the 5th byte, or the fifth byte within that block. All right, so what are we going to do with the example code today? So the first thing I need to do is to define a structure that's going to track each of the sprites. And I'm going to be changing the code to update the position of that single sprite to work with any of those sprites. In my code, I'm going to be calling this concept a game object. So instead of calling it a sprite necessarily, I'm going to be calling it a game object. Because the game object is also going to have the ability to know where to move and how to behave based on the logic of the game. And there are going to be 3 different types of game objects. We're going to take our ship that we have right now, and that's going to be one game object. The ship is going to be able to fire off a missile, so I've got a game object for the missile. And then we've got an enemy ship, and all the enemy ship is going to do is spawn at the top of the screen and move down, and it can be destroyed by a torpedo, or it will disappear when it gets to the bottom of the screen. Now I'm going to update the game object as well to generalize it, and I'm going to be using that game object concept to handle the game logic update. So I'm going to break it up into 2 steps. One I'm calling compute, and that will be the game logic in each of these game objects that's going to figure out what the behavior of that object should be based on what the gameplay should be. So it's going to compute where the game object should go, whether it blows up, whether it blows up something else, and so forth and so on. The other step that's going to be in here is that it's going to update for each of those game objects the sprite's position and whether it's displayed or not actually on the screen. So it's going to update the game it's going to update the computer hardware to update the screen to match what the game is doing at the moment. So it's kind of these two steps. We update, we compute, we update, we compute. The update, just as before, we're going to have that in the IRQ handler. And we're going to, again, wait for IRQs to come in before we do our compute processing. So I've drawn a little picture here over on the side to kind of illustrate what the game loop is going to look like. We wait for IRQ, and we compute, and we go back, and we wait for IRQ, and we compute. But at the same time, when an IRQ comes in, we're going to be doing the update IRQ handler for that. Then we'll generally finish before compute can happen. So essentially what's happening is wait for IRQ comes in, we update, and then we compute the new positions and everything else, and we go back and we wait for the next IRQ to come in. Now, why am I not computing actually in the update itself? That's mainly because compute in the end could take a long time to complete. It could end up taking longer than a frame, but we don't want to lock up the system for a frame or get two IRQs back to back because we've taken too long an update. So we want update to be as short as possible. And that's why we've separated out computing from updating, and we have just the update happening in the IRQ. So we're really only doing what we absolutely have to in the IRQ. And if compute takes too long, okay, so the objects don't necessarily update on the screen as quickly as they should, but that's probably going to be okay. But that's how it's going to look in the new code. All right, so let's pop over to the assembly code and take a look. All right, so the code has gotten fairly big for our example. So I'm not going to go through every single line of it, and not even every single file that I've put in here. So I'm just going to hit the main highlights and show the things that are relevant to structures and indirection. And if you're interested, you can go and look through the code, and I think it should be fairly understandable. So let's start off at the top level here with lesson 6, and you can see that I have broken out into several files. I have variables.asm, gameObject.asm, ship.asm, torpedo.asm, and flyer.asm. What I've done is the code that is relevant to, so let's say the ship is all in ship.asm, torpedo, for the torpedo game object goes into torpedo.asm. GameObject.asm is the common code that's going to be managing those game objects. And then variables is where I'm sticking all of my global variables and data types. So let's take a look at lesson 6 here. Most of this is going to be pretty similar. I have defined some locations in video RAM for the sprite data and so on. Nothing too terribly different until we get to this point here where we initialize the game objects and also the background screen. So I'm going to just completely ignore how bitmaps are working here on the C256 and how I'm doing the background image. I just added that in for some fun, but it's here in this file towards the end. You can take a look at it. There is an example of indirection there, but I'm going to skip over that for now. But for the rest of these, I'm initializing the game objects. I'm initializing the ship, the torpedo, and the purple flyer. For most of this, all that's really doing is loading the bitmap for the particular sprite into video memory so that Vicky can get a hold of it. Next kind of key point here is the actual game loop. So the game loop is much smaller, at least textually here, because I've pushed everything down into the game objects. So as before, I start off by re-enabling the IRQs with CLI, and then I wait for the interrupt to come in. And once the interrupt comes in, first of all, the soft handle will get called, but the other thing that will start to happen is that we will go and call into this game object compute function. And that is what's going to go through all of the game objects that we have in the system that are active and cause their compute function to run so that those game objects can figure out where they need to move or what they need to do next. The other thing that I do, the purple flyer, I don't have that on the screen all the time. there's a little bit of a respawn timer so that once it disappears, it waits for a little bit before it comes back. And this FLI tick function is just in there to kind of update the counter that says whether or not we should respawn the purple game flyer. And then I just do a branch back to the game loop. So that's all I'm really doing here, is waiting for the internet to come in, do compute, let the soft handler run to do updates, and update the timer on the purple flyer. The soft interrupt handler is looking pretty much the same as before, but whereas we just did the one update of the one sprite in the last example, now we need to do an update on all of the sprites. And to show how that's handling, first of all, let me pop over into variables and show you how this is laid out. So this is where I have my structures. So I have a structure here called HW sprite. This is representing the registers that Vicky has for managing sprites. So Vicky has something like 64 sprites, I think, quite a lot. And each of the sprites has 4 registers associated with it. So there's a single byte control register. There's a 3-byte address, which is really the offset in video RAM where the bitmap is for the sprite. And then you have 2 16-bit registers, X and Y, which are the coordinates where's that sprite located. The control register specifies whether or not the sprite's enabled, what the color lookup table should be for that sprite, and then where it is in terms of visual depth on the screen. How far back should it be? And so this structure is just representing those registers. And what will happen, and basically what it's doing is it's providing me with a convenient name for the registers when I'm needing to access an individual sprite's registers, just to make the code a little bit more readable. This could just as easily be handled with definitions where I'm defining an offset, but this I think is a little clearer. The question mark, I don't recall if I mentioned this in the slides. However, the question mark is indicating to 64 tasks that we don't really care what that value is at startup time. So this is, it's an unknown value here. There are times when you are working with the structures and you might want to set the values ahead of time. And there's a way that you can put that in, and I'll show that in just a second here when we get down to the next structure, which is GameObject. So this structure is representing kind of the game logic aspect of the sprites. So I have in here the notion of a type, and type is going to be 0 for unused. 1 is the player, the main ship. 2 is a missile that's being fired from the ship. And then 3 is an enemy ship, that purple flyer. I have a special type that I'm not listing here, which is if it's FFFF in the type, then that means that it's what I'm calling a sentinel game object. So I've got an array of these game objects, and I just found it convenient to have one more game object at the end of that array that indicates that I've hit the end of the list. Other things that I have in here are X and Y, so the location of the game object, DX and DY, which are the change in horizontal and vertical coordinates on every tick. So basically the speed, which way is it moving. Then I have a 4-byte variable HWReg, which is the address of the sprite registers corresponding to this game object. Now, some of you may recall that the 6586 has only 24 bits of address. So why am I using 32 bits here? The reason for that is really that it's kind of inconvenient. When you have a 3-byte pointer, it's a little inconvenient because you have to switch back and forth, the size of your accumulator, the size of your memory accesses as you're reading or writing the individual elements of this address. You either have to be in a byte mode the whole time and you write 3 individual bytes, or you read in 3 individual bytes, or you're going to be in 16-bit mode and take care of the lower 16 bits of the address and then have to switch to 8-bit to get to the high byte. It's a mess. So I'm wasting a byte of RAM here for this, but it makes it a little bit more convenient in terms of the code. Fewer times I have to switch the size of my accumulator. Then I have another pointer like that for the bitmap, so that's the location of the sprite in video memory. And then I have a 16-bit pointer, which is the pointer to the procedure that's going to do the compute step for this particular game object. So you can think of that as being kind of like a member function in an object-oriented coding scheme, and it's kind of where I've gotten the idea from. But we're really not doing quite object-oriented here. There's no inheritance or any of that nonsense. I've just got a pointer here as part of the game object so that I know exactly where to go to run that code. Then I have my definitions of my variables here. I don't think we necessarily need to go into any of these in specific except for maybe game objects. One of the things I did not point out in the slides is these, dword, word, byte, and so on directives. They can be used here in defining structures, but you can also just use it in regular, as if it were regular assembly code. And what they do here is that they allocate a certain amount of space in the memory that you're currently assembling. So we're starting here at 2000. And I say that old IRQ, that label is 2000, and I'm allocating to it 2 bytes. I have a question mark here because I'm not specifying a value there at startup time, but there are 2 bytes allocated to old IRQ. The next location in memory is going to be 2002, and that's going to be source, which is going to have 4 bytes associated to it. And then dest is going to be 2006. And so on and so forth. Other things that I didn't mention here are fill. So this is when you want to take, just basically grab a large chunk of memory and assign it to, a particular label. And in this case, what I'm doing is I'm taking the size of the game object, and I don't know off the top of my head how many bytes that is. I don't need to because I've got this size function that will compute it for me, and multiplying it by the number of game objects that I'm going to support at any given moment, which I think at the moment is 5. So that will allocate enough space for 5 game objects. And then I have another game object that I'm putting right after. There's that destruct that says, take this game object structure and place it in this location in memory. And one of the nice or handy things with structures in 64 tasks is that you can set them up to take parameters. So if you want to initialize some values, you can pass a value in when you instantiate one of these structures. You give it a name, is a comma-separated list that goes here. You give it a name, and then if you want to reference that name, you can do a backslash and the name. And so that will take whatever type value, whatever value I provide there, that first parameter is going to be called type, and it's going to be put here as the initialization value for type. So in this case, that's going to be FFFF, which is -1 for the game object type, and that's just there to indicate that we're at the end of the list of the game objects. So coming back to the lesson, here is a little loop that we've put in. So we start off, we take the address of game objects and we load that into X. So we're just working in that first bank 0, by the way, or in the current data bank, I should say. And game object is going to be somewhere in there, and we are taking that address and putting it into X. So X is going to be a pointer to our current game object, and we start with the first one, and we call game object update. So game object update takes a pointer in X for a game object, and it looks at that game object and tries to do the hardware, the update to the Wiki hardware registers for that game object. When it's done, we add the size of a game object to X. We're moving to that next game object. And then we look at the type code for that game object. So what I'm really doing here, I don't know if I've shown the syntax before, but this is essentially the indexed X address mode in the current data bank. So the comma B is a way of indicating that we're doing a 16-bit or databank relative addressing mode. And the dot, the comma X is then indicating that we are doing an index using the X register off of that. So we're taking the value of X and the value of the current data bank register and putting those together, and then we're adding on this offset. The offset in this case is 0. So we're going to look at that first byte of the first word of the game object record, which is the type. So we load that in, and so long as that's positive, so long as it's not negative, if it's a 0 or 1, 2, 3, whatever, so long as it's in that range, we keep looping. So we're going to keep calling game object update on all these until we hit that sentinel, at which point this is going to get a negative value. It's going to get FFFF. And so we'll fall out, and we'll mark that all the interrupts have been processed, and then we will return. So that's going to be our interrupt handler. So we're just going to loop through and call update on every single one of those. All right, so now that brings us to the game object code itself. So what is this doing? So we're going to ignore init for the moment, and new. Let's look at update for game objects. So game object update, the first thing it's going to do is it's going to grab the address that's in HWReg in the game object, and it's going to stick it in cur_sp. Cur_sp, if I come back to my variables, there it is. It's a pointer to the hardware sprite registers for whatever the current sprite or current game object happens to be. So I stick the pointer to the hardware registers there in cur_sp, and then I check the type of the game object. If it's 0, then the game object isn't active. Now, it may have been active the last time we called update, so the sprite may be somewhere on the screen, and if it's now inactive, just to be on the safe side, we want to shut it off. We want to deactivate it. And so what we're going to do is we're going to take a 0 and we're going to write it into the control register for the sprite. Now this syntax I'm using here, I'm using indirect index Y addressing mode for this. So cur_sprite is the pointer to the sprite hardware registers, and Y is the offset to the control register for a sprite. So that's a 0 pretty much all the time. And so I'm going to store an A into indirect, dereferencing that pointer and then adding Y. So that is going to write a 0 into that first byte of the hardware hardware registers for the sprites. A 0 in that control register turns off the enable bit and turns the sprite off on the display. And so if that's inactive, we'll turn it off and then we'll return. And that's all we're going to do for the update. On the other hand, if we have a positive value, or non-zero value, I should say, then we're going to come down here, and now we need to make sure that the sprites registers are correct for the game object. So just like before, where it might have been active just before, the previous call to update and is now deactivated, when we call update this time, it might be that it's active now, but the last time we called it, it was inactive. And also the bitmap might have changed, the location might be completely different. We need to change all the hardware registers to match the current state of the game object. So the first thing we do is we're going to write a 1 into the control register. So it's the same sort of indirection we had before. And now we take the bitmap address that we have in the game object. So that's the location of the actual image for the sprite. And we are going to write that into the address register for the sprite. Now here you can see I'm doing a little bit of monkeying around with the size of the accumulator. That is because the control register is a byte. The upper byte of the address in the Wiki is a single byte, but the lower is 16 bits. So I need to switch back and forth a little bit there. And then finally what we do is we set the X and Y registers in Viki for the sprite location. So what this will do is it will take that sprite, it will make sure that the sprite is displayed, and it will be in the right location, and it will make sure that the bitmap for the sprite is what's set in the game object. So basically, it will set the Viki registers to reflect the current state of the game object. All right, and if we come back to the game loop, we've got that game object compute. I should walk through that as well. So here is game object compute. And again, this takes X as a pointer to the game object that we want to do the computation on. So we take a look at, first of all, we take a look at the type of the game object. We check to see if it's 0. And now if it is 0, that game object is inactive, so we don't need to call a compute function on it. In fact, there's no valid compute function. So we'll just skip it and we'll go to the next game object. So we just add the size of the game objects to X and loop back. But if it isn't 0, then we need to check and see if it's a negative number. If it's a negative number, it's that sentinel again, and in that case, we are completely finished running this compute loop. So we can exit. But if it's positive, then the game object is active and it has a compute function. So what we do is we grab the compute function out of the game object and we store it in procedure. To come back to variables, procedure is the next pointer. So it's a 16-bit pointer to the compute function for the current game object. And then I'm going to do something a little funky. So what I'm wanting to do is I want to call that procedure. So I want to jump to the code that's at the address in the procedure variable. So really what I want to do is to do a subroutine call indirectly to procedure. Unfortunately, there's no indirect JSR available, but there is a jump indirect. So what I'm going to do is I'm going to do a JSR to this do jump label, which is down here. And all I do is a jump indirect to procedure. So what this does is the two memory locations, the 2 bytes starting at procedure have got a 16-bit value in it pointing to code. It's got the address of some code to run. So we will go, what the processor does is it goes to procedure and it pulls the 16-bit address there, and then it jumps to that address. It's not jumping to procedure, it's jumping to the code indicated by procedure. And when that procedure finishes and has an RTS, that RTS will return basically to here. So it will it will return to this JSR. So we JSR here and then we jump to the procedure. So it's a little funky there, but that's just, how the 65.8.16 is set up. So essentially all this game object update compute is doing is looping through all the game objects that are active, figuring out, and then calling the compute function for those active game objects. Now, if you're familiar with like 6502 assembly code or something like that, you might look at this and say, well, you could have just had a jump table, here and indexed it based off the type. And I could have, and that probably would have been a little bit more efficient. I did it this way for 2 reasons. One is to give you an example of indirect jumps. So it's a little artificial that way. But the other reason was this code, this gameObject.asm, it has no understanding of how the other game objects, of how the actual game objects work. It doesn't know a ship from a torpedo from a flyer, and it doesn't need to know. We provide that information actually in the game object itself. So it's a way of kind of isolating some of the code from each other. This isn't strictly necessary, but it's the way I coded it up here, and it's just an example. All right, so to complete this tour of the code, let's take a look at the Torpedo game object code, so you can see how an individual game object actually works. Here we have Torpedo init. This is just very simple. I'm just copying the bitmap for the Torpedo sprite into Viki RAM. So nothing terribly exciting here. I have then a launch function, which is going to be called by the ship game object when the player presses the fire button. And to support that, I have this torpedo count, which I initialized to 0. We're not going to want the player to be able to fire an infinite number of torpedoes. Maybe we wouldn't have like 3 or 5 or something like that. At the moment, I'm just limiting it to 1. So I load in the torpedo count, and so long as it is 0, then I'm okay. If it's greater than 0, or if it's not 0 rather, we're just going to skip the rest of this function. And so what it does next is that it's going to go and it's going to find an unused, an inactive game object slot in the array. I haven't shown this function. It's nothing really terribly exciting about it, but what it does is it finds a game object slot and that's not been used, and it puts its address into this goTarget variable. And so now I load that in, and if goTarget is 0, then we didn't find one. We have all of our game object slots are being used at the moment. So again, we don't want the torpedo firing in that case. So again, we can quit. But otherwise, goTarget points to a place that can be actually used as a game object for the torpedo. So we set the torpedo type. We point to the location in VRAM for that graphic, and one little this is a C256 quirk. Vicky, when you're providing it with an address in one of its registers, it's always wanting the address relative to the start of video RAM, not to the start of the CPU's memory space. So I need to take the address of the torpedo VRAM and remove, subtract away the start of the video memory address, and then stick that in in the game object. I take the address of the compute function for the torpedo and I stick it in there in the computer member. I set the initial X and Y, which are provided by the ship, and I set up the initial velocity. So we're not moving horizontally, so 0 in dx. And we're going to move up 4 pixels every tick on the torpedo. And so I set a -4 into dy. And then I increment the counter for the torpedoes just to indicate that we've created one. So now when update gets called on the next interrupt, this torpedo will appear on the screen and will start doing its thing. But what is its thing? Well, that's going to be handled by compute. So what the torpedo does is that it moves up from its initial starting position. If it gets to the top of the screen, it's going to turn off and clear itself out. If it hits a purple flyer, it will destroy both the purple flyer and itself. So, first thing to do is we're going to calculate its new position. We get the current Y value, so the current row it's on. We add its Y velocity, and we store that back in Y. So the next time update gets called, the sprite's position will be moved up by dy rows, which is going to be 4 in our case. Now we also want to check that Y value, and if it's 0, then we want to disable the torpedo. So if it's reached the end of the screen, if it's gotten to the top of the screen, we're going to turn it off. But then the next thing, now what we need to do is a little bit more complicated. We need to go through and find out if it's colliding with one of those purple flyers. So we're going to start off with the game object, the first game object. So we get the address of the first game object in A, and we're going to store that in goTarget. So goTarget is a variable that I'm using as a pointer to a game object that is kind of our secondary game object. X is pointing to whatever game object is currently functioning, and goTarget is, generally speaking, is kind of the secondary game object. So we start off. We load the type of the game object, and here you see I'm just doing an indirection here to get that first word. If it's negative, again, we've hit that sentinel, and so we're done with our processing here. But if it's positive, then we want to check and see, is it a flyer? If it's a flyer, it's a potential collision target. And if not, it's the ship or another torpedo or something, so we can ignore it and check the next game object. So if it's not a flyer, the type is different, we come here and we add the size of the game object to go target, and we go back and loop on and check on the next one. If it is the flyer, then we're going to want to check and make sure that see if we've got a collision. And the way I'm doing that is kind of a simple hitbox comparison. I'm just checking to see if within if we are within 16 pixels left or right or top or bottom of each other, and if they are, then we'll hit. So here's the flyer test. We're going to check first horizontally. We get the torpedo's X position, and then here we get the X position of the target, so the potential collider. And I'm going to subtract one from the other and see if that difference is less than 16. Now, that might be a negative number, so I want to take the absolute value of it. So if I've got a 0 or higher, if I've got a positive value, I'm just going to go in here and check to see, if it's greater than or equal to 16. Or sorry, if 16 is greater than or equal to the difference between them. Otherwise, what I'm going to do is take the 2's complement of that difference. So basically this portion here is absolute value. So I'm taking the absolute value of that difference. So if the absolute value of the difference between them is less than or equal to 16, it is a possible collision, and we'll go and check the Y values. If the difference is greater than or equal to 16, and we know we don't have a collision, and we can check the next game object. So we go back up here to increment go target. Otherwise, we're going to do the same sort of test on the Y values on the current row. If both the horizontal position and the vertical positions are within 16 pixels of each other, then we have a collision when we come down here. What we do here is we call this fly kill function, and so that's something in the purple flyer. And what that really does is that disables the purple flyer, so it's going to mark it as inactive, as an inactive game object. And it's also going to update some values in the global variable so that we will eventually respawn a purple flyer later. So essentially that's destroying the purple flyer. And then we also disable the current game object, which is the torpedo. And we decrement the torpedo count. So when this is finished and the next update happens on the interrupt, then both of those sprites will disappear. To make an actual game of this, we probably have some sort of score counter. We'd update that score. Maybe we'd have some sort of collision or explosion animation that we turn on. That would all happen. That would all get queued up here. But that's really it. The purple flyer code, it works in a very similar way. The ship works in a similar way, and so that's kind of the code there. Certainly more I could talk about there, but this is already running into a very long video at this point. So let's go into the actual game and give a little quick demonstration of that. All right, I'll now send the game over. Get my joystick. So here you can see, there's my ship moving around. There's the purple flyer, and I can press the fire button and send a torpedo off. You see I can only fire once, but I could change that. And now if I come over here and I shoot, you can see that I can destroy both of those sprites with a torpedo. And the game objects all move independently of each other, which is all handled quite naturally by the way that the structures and the indirection work together. So there you have it. All right, so this will probably be the last video in this tutorial series for 65.8.16 assembly code. I think I've pretty much covered everything that I wanted to cover as far as how that processor works. There are certainly, instructions that I haven't talked about, and maybe some best practices and things like that, but I don't know how useful that would be at this point. I may continue the tutorial series, but get more into C256 specific things, talking about Wiki and interrupt controllers and how the sound chips work and so on and so forth. But we'll see where that goes. But anyway, I hope you enjoyed this series. I hope it has proved useful to you in some way. And thank you very much for watching.